Good morning. Can you guys see well?
Yeah.
Yep.
Yes.
You can, you can either use the chat or you can unmute yourself and talk. All right.
Right.
So we still have 3 minutes. I'm waiting for other students to join in. I hope you had a good break. I doubt it. So the way we are gonna do it is I will try to run it exactly the same way I ran the class. So at the beginning, I expect questions from you from the previous homework. And I will answer your questions as usual. And then after that, we will go through the new material. So I expect you to have to come with questions every time. I will go over it so you know how to solve the problems, and then we proceed as usual. So do you guys have any questions? I have 2 minutes to kill.
How will quizzes be done from now on?
My plan, and I hope it's gonna work, you know, this week everything is gonna like trial week. So my plan for this week, you guys, the quiz will be on Blackboard at like 10:30 or 10:25. You take it. It should be a short quiz, like 15 minutes at most. And you take, you know, you download the quiz. You take a neat sheet of paper. You write the answers clearly on a piece of paper, and then you upload it into Blackboard. Can you guys do that?
Yeah.
Yeah, that's how it's gonna take. So I'm gonna give you like a 15 minutes quiz. It's not gonna be like a long quiz or anything, like 15 minutes quiz to make sure that you guys are on the top of the material. So you download it and you take it. You don't have to print the quiz at all. You take a neat sheet of paper, you write the answer on a sheet of paper, take a picture and upload it into Blackboard. And we see how it works. If it works well, that's the way we're gonna go. If it doesn't, I hope it does, then I will think of something else. Make sense?
If
Yeah.
Yes.
Yeah, so that's how it will work. It will be a short quiz. Just make sure that, as I said, you know, I want you guys to basically keep up and learn the material.
If it doesn't allow us to turn it in online, can we just email it to you directly?
You know, I would rather online, otherwise I will have tons of emails.
Yeah, I know, but I'm just saying, like, just in case, like, when I try and like submit a attempt, or I submit like an image and it won't let me attach it, is it okay if I just like?
Yeah, in the worst case scenario, you can. But
Right.
I really want them on Blackboard. I will have a nightmare if every one of you and my other student handed by email. It's not, doesn't work. So
Right.
I really want it to be on Blackboard. Okay, so what I'm gonna do actually, what I'm gonna do with other classes, I will like tomorrow send you like a fake quiz. Okay, so you can practice, just make sure everything goes smoothly. So tomorrow you will get something fake quiz. You just download it. Basically, it's gonna tell you write your name. So you write your name on it and just you upload it into Blackboard and see if it runs smoothly. And if everything goes fine, then we will go exactly the way I'm telling you to. Any other questions? It will be around 10:30, and you will have like 15 minutes to do it. So I will give you like 20 or 30 minutes, but the quiz, as a quiz, will take only 15 minutes. You will have 30 minutes to give you enough time to download it. Oh, sorry, enough time to upload it. Any other questions? James, did I answer your question? James? Yeah, all right, anything else? Okay, so we get started, and if you guys have any questions, please feel comfortable to either email me or during my office hours that you guys have the URL, just, you know, ask me questions. You know, feel comfortable, to ask as many questions as you want. We are all in basically uncharted territory right there. All right, so as I said, we start first by answering your questions. Did you guys do the homework?
Yeah.
Okay, questions.
I don't got any.
Oh, anybody else?
The homework from 312.
From, yes, exactly, section 1.8.
For either question 14, 15, or 16, it asks to draw a graph or like a geometric representation, and
Yes.
I was unsure how to do that.
14, 15. Okay, so 14, let us say number 14. Okay. Now, if I need to lift the paper, you just write to me on the side, lift the paper, just in case I didn't pay attention to those details. So let's take number 14, for example. They use a rectangular coordinate to plot U and V under images under the given transformation. Remember that if you have a transformation T from any place, Rn to Rm, that's transformation, which is nothing more than a function. Then if U in Rn, that's my vector, T of U is what we call the image. That's what we call the image of U under T. It's just, as I said before, it's just like a sophisticated way to say that's the output. So we call this the image of U under T. So in this problem, we have the following function. So we have a function from R2 to R2, and it's given by the following rule. T, it takes a vector, basically, since it's in R2, it means the vector has two components, and it takes that to the following, times x1, x2. So that's 0.5, 0, 0, 0.5. So that's my transformation. So the question is, find the image of the vector 5, 2. So that's 5, 2. What does T do to it? Takes this matrix and multiply it by 5, 2. So 0.5, 0, 0, 0.5. So we just multiply. So it's 0.5 times 5, which is a 1. And this is, sorry, yeah, 0.5 times 2. It means it's a half. What am I doing? It's so that's the 5 halves. And half times 2, that's 1. Okay, that's the image. Now, if I find T of -2, 4, that's exactly the same thing. So that's really how the function acts. It takes the matrix A and multiply it by the vector -2, 5. Okay? But now let us really understand, what does T do to a vector, any vector? I'm not going to restrict myself to those. I'm going to think about what T does to a vector. So what does T do to it? Any vector, because if you understand, it's easier to understand that. x1, x2. That's 0.5, 0, 0, 0.5. So this is equal to what? It's 0.5 x1, 0.5 x2. Correct?
Yeah.
All right. Now I'm going to factor out 0.5 because I can. So it's 0.5 times x1, x2. Why doing this is very helpful in this problem? Why doing this is very helpful? What is T doing?
It's scaling.
It's scaling it, exactly. It's 0.5 times the vector. So what T does is scaling the vector. So now I can show you exactly what T is doing. So this is my vector. Let's actually stretch it like this. That's x1, x2. What's T? It's half of it. So this is, so it takes the vector and actually scale it down by a factor of a half. That's the geometric effect, sorry. That's the geometric effect of this transformation. So you can actually call this matrix the scaling matrix. because what it does, it takes a vector, and the only effect of it is to scale. So if I, instead of 0.5, I put a 2 here and I put a 2 here, what's going to be the effect of it? It's just stretch it by a factor of 2. All right? Does this make, does this answer your question? Okay. Now, number 15 is actually, we look at number 15. Again, we have to look what is geometrical sketch, what that does to a vector. So the easiest way is to study what it does to any vector in general. So suppose I have a t, and in number 15, t is from R2 to R2. And what it does to a vector, so it's take the matrix, multiply it by a vector. That's really the rule. And this is 0, 0, 0, 1. So if I compute, what's the output? I will have 0 in the top, and I will have x2. So what is t doing? What
Giving
is
you the
t?
x2 component of the vector.
Right, so this is my vector x1, x2. And it gets rid of the x1 component, but geometrically, who can tell me what it's doing? What is the image?
It's on the x2 axis.
It's on the x2 axis, right? And where is it? Do we know exactly where it is? It's right there. Does make sense? This is x2, and this is x1. It's right there. So what can you call this matrix? What can you think about that? What is t doing to the vector? Does anybody can think of the right name?
Is it a projection?
Exactly, that's the projection. It's projecting it into the x2 axis. That's what is taking the vector x1, x2 and really projecting it into the x2 axis. That's what this matrix is doing. And actually, we're gonna call this matrix, you know, people give this matrix a name. And this matrix called the projection matrix. That's called the projection matrix. Because what it does, it takes a vector and actually projects it into the x2 axis. Okay, so those matrices definitely have geometric interpretation. They do things. They do things to a vector. They reflect it, and they rotate the vector, and here they are projecting the vector. All right? Any other questions? Okay, let me ask you one question just to make sure you guys remember the terminology. Suppose t is a function from whatever, R2. I'm going to look at number, for example, I'm going to look at number 11 just to put the problem in a good language. So I'm going to look at number 11 on the problem I assigned. And this is the problem. I have t is a function, and I will not write as usual. I'm not going to tell you what this is, and I'm going to tell you what this is because you have to tell me. And t is given by the rule t of x equal a times x, where a is, so it's a times x, where a is the following matrix: 1, 0, 2, minus 4, 1, minus 6, 7, so that's number 14 in your, number 11, minus 4, 6, and minus 5, 3, minus 4. Okay, so question number 1 to you before I go back to number 11. I want you to tell me what goes in each one of those squares here.
The first square should have a 4 in it, and the second one should have a 3.
Do you guys agree with him?
Yes.
Do you agree? Yeah, because we want the multiplication to make sense. For the product to make sense, I need 4 entries here. So my x here, that's my input, have to have 4 entries. And the product, which is a times x, that's my output. Now my output is going to be, that's a 3 by 4, 4 by 1. My output is in R3. So I have a function that is from R4 to R2. All right. Now the question is, suppose I have a vector B, which is -1, 1, 0. And the question is B in the range? Now I want you to tell me, what does it mean in the range of T? What's the definition of something in the range? Okay, anybody? Before I pick, I can pick.
Is B a vector that's able to be represented in R3?
That doesn't mean in the range. It is in R3.
Is it
It is in R3. It has 3 components. What does it mean in the range of T? So
Can
T
you obtain-
is from R4, that I don't know how to draw, all the way to R3. That's my T. And my vector B is -1, 1, 0. So it's gonna go somewhere this way, that way. And suppose this is my vector B. What does it mean, B in the range? I want the exact definition.
Is it possible to get a vector x to get like multiply it with a to get to b on the
Absolutely correct. It means, can I find a vector? Can I find a vector here such that when I take T of this vector, it means A times X, I get the vector B. It's like the range in calculus 1 or pre-calculus. It means, is it an output value? It means, can I find a vector X such that T of X or A times X is equal to B? So is B in the range? So what's the definition? It means, can we find vector X in R4 such that, that's what in the range, T maps the vector X to the vector B. That's what's in the range. Can I find something that go to the vector? It means, can I find B such that A times X equal to B? Because that's what T of X is. It's A times X. Can I find X so that A times X equal to B? And now we're back to basically solving a system. So I go back. I'm going to look for find X such that if I take the matrix A and time it with X, X is X1, X2, X3, X4. Do I get the vector B, which is -1, 1, and 0? And this is 1, 0, 2, -4, 1, -6, 7, -4, 6, -5, 3, -4. That's really what the question. Can I find a vector X which is mapped into the vector B? And to do that, we do the regular thing. We take the augmented. Okay, let me pick up a nice piece of paper because I can't finish here. So I take the augmented matrix, 7, -4, 6, -5, 3, -4, and I solve it. I solve it for the input. So now the solution is the input X that goes to the output -1, 1, 0. So I take this and I do what we always do. We reduce and I get the following. 0, 1, 0, -9, -4, 0, 7, 3, 0. And my last column is 3, 1, 0. Okay. Okay, with this picture, am I going to be able to find a vector X? Yes or no?
Yes.
Yeah,
Yes.
because my system is absolutely consistent. And actually, how many vectors are going to be mapped into the vector B? Is it 1? Is it 2? Is it infinitely many?
Infinitely many.
Absolutely. So not only one vector will be mapped to B, so it's consistent, of course. So consistent, it means B in the range. Means we can find a vector in the range of T. And more than that, actually we can find infinitely many vectors, not only one. A lot of vectors are going to be mapped into the vector B. So if this is the picture right there, it means I can find a whole slew of them. We can basically describe them. I can find whole slew of vector Bs that all of vector X's, a lot of X's, which are going to be mapped into the vector B. A lot of X's will be mapped into the vector B. Any questions? All right, so now I'm going to move to, along the same idea, the linear transformation, but now we're going to introduce the idea of linear transformation. Now, as you guys know, the lecture is on Blackboard, so I'm going to not rewrite it because that's going to be really hard. So I'm going to go through the notes, right, explaining every aspect of it. Now, I promise you to write bigger next time. So, suppose we have a transformation. It means a function. Don't give the word transformation more meaning than that. It's just a function. What does it mean to be a linear transformation? So I'm adding the word linear. Linear transformation if this function t satisfies the two conditions. If you take two vectors, t of u plus v equal t of u plus t of v, means the image of the sum, if you take two vectors and you add them, and then you find where they go, where they are mapped to, is the same thing as taking the vector u, finding its image, and adding to it the image of the vector v. So t of u plus v is t of u plus t of v. And this is for all vector u and v. The second condition it should satisfy is that the image of a scalar times a vector, if you take a vector, scale it, and find its image, is the same thing as scaling the image. Before we start working with that, this should remind you something. Somehow we've seen linearity in your classes, but we never mentioned the word linearity. Let me remind you of something which is linear, in a linear operator. When you take two functions and you find their derivative, what do you get? The derivative of the first plus the derivative of the second. You take a function, you multiply it by a scalar, and then you differentiate. You can basically take the scalar out times the derivative. We say that differentiation is a linear operator because derivative of the sum is sum of the derivative, and scaling a function then differentiating is the scalar times the derivative. So we say that differentiation is linear. So transformation is linear if you take two vectors, you add them, then their image is the sum of the image. You take a vector and you scale it, then you find its image. It's like taking the original, finding the image of u, and then scale it. So picture-wise, that's the picture. I will draw it here much bigger. The first property, what's the picture of it? T of u plus v is t of u plus t of v. What does this mean? It means the following, picture-wise. Suppose it's a vector u. And, no, sorry, I'll take a bigger, another paper. So, that's the picture. This is my t, and this is my u, and that I said this is my v. T is going to take t of u to here, so that's t of u, and that's t of v. What does this property tell you? at least geometrically. It means if you take u plus v, the sum, you're creating a new vector, u plus v. Where does t map u plus v? It maps it to t of u plus t of v. It means that if you know where u and v goes, you know immediately where u plus v go. It goes to the following. You take t of u plus t of v, and you take their sum. This vector here, that's t of u plus v. It's the same as t of u plus t of v. So basically, if t is linear, and you know where the vector u goes, you know where v goes, you know immediately where their sum goes. It just goes to t of u plus t of v. We say that t preserves vector addition. Okay, so sometimes we can read it that the image of the sum is the sum of the image. Now, what does the second property tells you? Tells you that if the image, if you take a vector and you scale it and find its image, it's the scalar times t of u. Okay, so what does this mean graphically? Means this is a t, and that's my vector u, and that's the image right there. That's where t takes it. If you scale u by factor of 2, where does this vector go? If this property is satisfied, where does this vector go? Where is its image? It's twice t of u. So this is point here is twice t of u, and this is t of tu. So you take a vector, you map it. If you scale it, where does 2u go? To 2 times t of u. That's what a linear function is. And we're gonna see a lot of them. So that's the geometry of it. So first we're gonna learn how to work with linear function, and then example of linear. I mean, do they exist? Do we have functions that satisfy this? So my first problem is simple. How to work with linear transformation. So suppose I have t from R2 to R3. And I didn't give you much info about it. I just told you that it is linear. And I gave you 2 vectors. I tell you that, I didn't even tell you what the vector u is. I tell you that t of u is 1, 2, 3, and t of v is -1, 1, 4. So now my question, can you find t of 2u? Linearity and this condition. Can I find t of 2u? What do you think? Can we do that? If linear, what does this mean? If I scale the vector u by 2, t of 2u is twice t of u. That's what linearity tells me. It means I can take the scalar outside. Now, if I know t of u, it's 1, 2, 3. I multiply it by 2, I get 2, 4, 6. So we using the fact that if t is linear, t of 2u is 2 times t of u. It means I can take the scalar outside of t. Now, can I find t of 2u plus 3v? What do you think? Help me out. So, t of u, I write it in big, is 1, 2, 3. T of v is -1, 1, 4. T linear. And now I want to find t of 2u plus 3v. Can I do that?
Yes.
Yeah, let's do it. Because it's linear, what does it mean? T of the sum, image of the sum is sum of the images. It means I can break this way. With me? Now, if t is linear, it means I can take the scalar out. So that's 2 times t of u plus 3 times t of v. Okay, that's how we're using linearity. Now, I know what T of U is, so that's how we work with it. And I know what V is. So now I know where 2U plus 3V is. I just have to add those numbers. I will have 2 minus 3 minus 1, 4 plus 3, that's a 7, 6 plus 12, which is 18. So that's how we work with linearity. Okay? So the benefit of linearity, if we know that this transformation is linear, is that if I know only U and V, I basically can find the image of any linear combination of them. So any scalar times U plus scalar times V, I will be able to find its image. So are there functions which are linear? And are there functions which are not linear? So that's really what we're gonna talk about. So the first rule, and as I said at the end of my lecture, is that if my function is linear, then we have in general T of C1U plus C2V. So if C1 and C2 are two scalar, is C1 times T of U plus C2 times V of V. So if you know U and V, if any linear combination of them, it's C1 T of U plus C2 T of V. Now what we're going to proceed to is the following. Example of linear transformation. Do they exist? And the example of transformation that they are not linear. That's what we're going to do now. Okay, so my first example is, and I'm going to rewrite it because my handwriting is small, and next time I will have it bigger. So now I'm going to take the following function. It takes x1, x2 to x1 plus x2 and to x2. That's my t. And I'm going to convince you that this is linear. This is actually a linear transformation. So first, let us remember that my t here is from R2 into R2. So what does it mean, linear? So I have to convince you that if I take two vectors, u and v, this is the same as t of u plus t of v. All right? So let's see if this is satisfied. So I'm going to take my u, it's u1, u2. And my v, I'm going to call it v1, v2. And somehow I want to show you that we can break the t. So let us see what this gives me. So this is u1 plus v1, and this is u2 plus v2. All right, this is equal to what? What does t do to a vector? It adds the first component plus the second. So it takes the first component, add to it the second component. And then what it does, it takes twice the second component. My goal is to convince you that this is the same thing as taking t of u by itself plus t of v by itself. That's what I'm going to convince you. All right, is this possible? Are you trying to think with me a little bit? What am I supposed to do to convince you that this is the same thing as t of u plus t of v?
You could just solve t of u and t of v the same way you just did t of u plus v.
Okay, that's a good idea. So I'm going to do what your classmate mentioned. Do each one separately and see if they are equal. That's natural way. Okay, what's t of u? T u is u1, u2. And v is v1, v2. So let's do that and see if we get the same thing here. So that's u1 plus u2, because that's what my function is doing. And this is twice u2. This is v1 plus v2, and this is twice v2. Okay, and we're almost done. I'm going to add them now. So u1 plus u2 plus v1 plus v2, and this is 2u2 plus 2v2. Am I getting the same answers?
Yes.
Am I getting? Watch. u1 plus u2 plus v1 plus v2, that's the same thing.
Yeah.
That's 2u2 plus 2v2. So if I just factor out the 2, I will get exactly the same. Check. Property 1 is checked. We're going to learn how to do this problem way, way faster, but that's fine for now, just to understand what we're doing. Now, the second property. So now I satisfied the first property. This is called T preserves vector addition. That's what we call this property. Now, the second one, does it preserve what we call a scalar multiplication? It means, can I actually take the scalar out of it? That's really what's then. Can I take a scalar out in here? All right, let's do that. So suppose again, my vector is u1, u2. And so c times u, multiplying its vector by a scalar, means multiplying each component by the scalar. So now let me compute T of Cu. Okay, this is equal to T of Cu1, Cu2. All right, what does T do to a vector? Okay, what it does? It adds the component, and then it takes twice, the second entry is twice the second component. All right, now I want you to look at this. And the question is this equal, that's my question mark, C times T of U? It means, is this equal to C times U1 plus U2 to U2? That's really what I'm after. Basically, can I factor out the C? What do you think?
Yes.
I factor it out here. What do I get? U1 plus U2 and 2U2. This is absolutely T of U. So this transformation satisfies this magic condition, which is called the linearity condition. All right? Now, we're going to see a lot of linear. That's what this course, the course is called linear algebra anyway. Now, can I find, so a transformation, I'm going to give you an example of a transformation that's not linear. So I have them in my note, but I'm going to rewrite again here bigger. As I said, promise you next time you'll have bigger, larger notes. So I'm going to take the following, and I want you to think with me as I am working. I'm going to take T from R2, let us say, to R2, and it does the following. It takes a vector x1, x2, and it does the following to it. It multiplies, that's the first entry, and the second entry is x2. And this is not a linear transformation. How do I convince you it's not a linear transformation? Let us go back. What does a linear transformation satisfy? Linear transformation has to satisfy two properties, two major properties. It has to satisfy T of U plus V equal T of U plus T of V, T of C times U equals C times T of U. To show that it's not linear, it suffices to give me an example where one of them is not satisfied. Okay, give me an example. It means either you give me two vectors, U and V, such that this property fails, or you can give me a scalar and a vector example to show me that the second property fails. So to show it's not linear, you just have to give me an example to show me, you know, which one fails. So let me focus on that. Usually it's easier to start by showing that this property fails. So we're going to show that this property fails. Okay, I'm going to do it by example. And you're going to provide me with an example. Because I want you to give me a scalar C and a vector V sorry, a vector u, such that this property fail. I'll give you 2 minutes to do it, and then I expect an answer. So I wanted to find scalar c and u, example, such that this property fail. By examples. All right, get going. The one who's ready, just let me know. Okay, anyone?
You can choose like C to be 2.
Let's
And
choose
then-
c equal to 2. I'm listening.
And then just say U is 1, 2.
1, 2. Okay. Let's see if this example works. So I'm gonna take t of cu, and I'm gonna take 2 times c of u, because his c is 2, and see if they work. All right. Let's see. T times cu, according to your classmate, let's see what's cu. So it means t times 2u. It means t times, sorry, t of, now what is 2u? It's 2, 4. Okay, what's t of 2, 4? What does t do? Multiply the entries, it means 8, and it keeps the second one by itself. What if I take the 2 out? Will I get the same answer? Okay, let's do that. So it's 2 times t of the vector 1, 2. Okay, which is 2 times what? What does t2 do 1, 2? It multiply, which is a 2, and this one keep it by itself. So it's gonna give me 4, 4. So definitely t of 2u is different from t of u. So my transformation is not linear. Okay, now that's not the only example. You can give me a lot of other examples. A lot of other examples. All right? Now, what's happening mathematically? Why this is failing? So what I'm going to show you now, that what's really going on in this example that makes this property fail. So let us see it in a more abstract way. So let me go back to the same example. So I have t of x1, x2 equal x1, x2, and x2. Why the property fail? Watch carefully what's happening. When I take c times x1, x2, that's really what's happening in general. It means t of cx1, cx2. So this is going to give me cx1 times cx2, because I am multiplying, over cx2. Okay, what does this give me? C times c, c squared, x1, x2, and this is going to give me cx2. The idea is, can I pull the c out? If I take c times t of x1, x2, I'm getting c x1, x2 over x2, which is, if I multiply it out, I get that. So what's really going on here? Why? What's causing the linearity to break? Can anybody see it? This entry is the same, correct? The problem is here, because the x1, x2 are multiplied. When I took cx1, cx2, I multiplied cx1 times cx2. This really brought me the c square x1, x2. However, in this case, when I multiply c by the output, I get c times x1, x2. So those two, the first two entries are actually not the same. That's really so. I was not be able to put the c. If I pull a c, I still have the c inside in here. I cannot really get it out. So that's what's happening in the general scenario. But to show that it's not linear, we don't always have to show it in general. You can, if you want. You can just give me an example and show that the linearity is actually fake. All right, I'll give you another example, and I want more students to answer. So, another example of a linear transformation, a nonlinear. So I'm going to take t x1, x2 equal x1 plus 2 and x2. All right, I want to show me that it's not linear. I give you 1 minute, and then I want the answer. Not linear. It's usually the easiest way, the easiest condition to show that fails is this condition. So I want a scalar and a vector to show that this one failed. Okay, who's ready?
I'm ready.
Okay, go ahead.
So you just want like another c and another vector u, right?
Exactly. I want the same thing to show
Okay.
me that this failed. There are
Then,
tons of examples. Just whatever. Go ahead.
No, the same thing as last time. Then just c is 2, and then u be x be 1 and 2.
It will work. I don't know. Not everything works. So you want C to be 2,
Yeah.
U to be 1, 4. I don't remember what you picked before. Let's see. Does it work? All right. T of 2U is T of 2, 8. It means, what's T of 2, 8? What does T do?
You would get 4, 8.
4, 8, is he right? It's the first component plus 2. And yeah, so it's 4, 8. And what about 2 times T of U? It's 2 times, what's T of 1, 4?
3, 4.
It's 1 plus 2, right? And 4. It's 2 times 3, 4. It's 6, 8. Absolutely not linear. Did it look like linear to you?
At first I thought it was.
Yeah, at first it was, exactly, because you have x1, you have x2. So what caused it not to be linear?
Is that constant that you're just adding it
It's
to it?
that's constant. That's constant. So let me show you the picture in a more abstract way, and then we start making some rules. Yes, it's the plus 2. Alex, you're right. It's the plus 2 that's really giving me a problem. So let me show you the picture in a little bit more abstract way so you understand what's really happening mathematically, why the linearity is failing. So I'm doing now the abstract version of it. As far as you are concerned, you give me an example, I am fine. But I like to show the abstract idea so you understand how things are failing, how it is failing. So suppose I take the following vectors, U1, U2, and I'm gonna compute T of CU and C times T of U and see what's happening. All right, what's T of CU? It means T of multiplying U by C, it means multiplying each component by that. All right, so this is gonna be equal to the first component, that's the rule, you add 2 to it. And this is C of U2. Am I right?
Yeah.
Yeah, I think so. Because what's the image of that? It's the first component Whatever the first component to it, you add 2 to it. The second entry is the second entry of your vector. So this is going to give me that. What about C of TU? Can you guys see what's going to happen now?
Yeah, that 2 will have a C this time.
Right. This is going to be T of U1, U2. It means C times, what's T of U1, U2? What does T do? U1 plus 2 and U2. And if I factor out the C here, I will get CU1 plus 2C over CU2. Definitely, those are different from each other. This 2 still hanging and this 1 is not. So these are examples of linear and nonlinear transformation. Now, some important idea that we're gonna, save some of the work, not all of it. It's gonna save some of the work on it. All right. So the first theorem here, I'm saying that. Okay. So that's a rule. If T is linear, then T will take the 0 vector to the 0 vector. So linear transformation, so if T is linear, then the 0 vector has to go to the 0 vector. Now the proof is a bit abstract. It's one of the abstract proof of the course. Very simple, but abstract. Let me tell you why, and you help me out. Suppose I take T of 0 times U. T of 0, sorry. I'm going to write 0 as 0 times U. Is that correct? But this 0 here is a what? That 0 here is a scalar. And that's a vector. If T is linear, it means I should be able to take the scalar out. That's the linearity property. It's a bit an abstract of a proof. But now 0 times that, so this is a scalar, 0. And this is a vector. Scalar times that, that's the 0 vector. So T of 0 equal to 0. So if T is linear, T of 0 has, T should send the 0 vector to the 0 vector. So every time, so whenever.
I have a quick question about that.
Oh, please, go ahead.
Okay, so as for the rule, like the rule states T is linear if the transformation of the 0 vector is equal to the 0 vector, correct? That's
a theorem. That's not the definition.
All right, okay. So when we tackle a problem in order to define if it's linear, are we allowed to have the knowledge that we can break the 0 vector into like a regular vector and the 0 as the scalar you are just doing right now?
Yeah, yeah.
Okay, all right. Just wanted to make sure.
So whenever, all right. So if a function is linear, then it has to take the 0 vector, 0 vector. So whenever T of 0 is not 0, what can you say immediately?
Not linear.
That T is not linear. And this helps you a lot. All right, so I'm going to go back to the example I did a minute ago. So let me take this following example. I showed you why it's not linear by doing the whole work. But now I'm going to show you a quicker way. This is x1 plus 2 x2. Okay, we know that it's not linear. We actually did a lot of work to do that. But now watch this case. What is T of 0, 0?
And 2, 0.
2, 0. It's definitely not the 0 vector. So you can say immediately not linear. So now you have 2 ways to convince me that this is not a linear transformation. Okay? However, if T takes 0 to the 0 vector, then it could be linear or not linear. I have no idea. Then could be linear or not linear. But if t of 0 not 0, automatically not linear. If t of 0 equal to 0, then two cases. It could be linear or not linear. We will have to decide. Remember in calculus 1 or pre-calculus, suppose I take this function f from R to R. And the simple linear function that we learned, f of x equal mx plus b. When can we call this function linear using the definition of linear algebra? Who can answer the question? You guys call it linear, but actually mathematically this is not called a linear transformation. What's causing the problem? When will this be a linear transformation?
That function would be a linear transformation when b would be 0.
When b equal to 0. If b is different from 0, this is not linear. Absolutely. This is not linear if b is different from 0. Actually, when b is different from 0, this is, we call it affine transformation. We don't call it linear, you know, in more advanced courses. Linear, this is failed the definition of linear as far as linear algebra is concerned. We usually call it an affine transformation, not linear, when b is different from 0. Just as a side remark. All right. Now, what we're going to show is the following. The most important transformation we work with in this class are what we call matrix transformation. And let us remember what a matrix transformation is. So matrix transformation are those functions which are given by the rule t of x equal a times x. This is what we call matrix transformation. Now what I'm going to show you that every matrix transformation is linear. It means those and there are a lot of them, you know, it means like the projection that we saw a minute ago, that's linear because it's obtained by a matrix. Dilation is linear. Reflection is linear because all those we got them by the rule t of x equal a times x. So I'm going to convince you now that every transformation given by this rule is automatically a linear transformation. So let's see why. So suppose t, again, let's say from Rn to Rm, is given by t of x equal a times x. Okay, then t is linear. Means it has those nice properties. And let us see why. So I'm going to take two vectors. So the first property, t of u plus v. And I'm going to show you that this property holds. So what is t of u plus v? What does t do? Remember, t is a times x. That's the output. So it's a times u plus v. That's what it does. This is a matrix. U plus v is a matrix. U is a column matrix. V is a column matrix. Now we use the property of matrix multiplication, which tells me that I can distribute. So this is going to be A times U plus A times V. Now I'm using the property of matrix multiplication. But A times U is itself T of U plus T of V. So multiplying by a matrix, if my function is given by the rule, it takes x to A times x, the first property is automatically satisfied. The second is satisfied as well, because what does the T do to C times U? Takes the matrix A and multiply it by CU. Again, I'm going to use the property of matrix multiplication. C is a scalar, so it's C times A times U, which is C times T of U. So every matrix transformation, means every function given by this rule, is automatically a linear transformation. So all those geometric transformation we worked with, reflection with respect to the x1 axis, to the x2 axis, the projection we just did a minute ago, the dilation and the shrinking, the scaling we did a minute ago, all those are linear transformation. And this property is going to help me to show that a transformation is linear without having to do a lot of work. So let's see what I mean by that. So I'm going to go back to one of the previous examples. Go back to one of the previous examples. So one of my first example was t of x1, x2 equals x1 plus x2 and 2x2. Do you remember this example? Do you remember we've done this example? And what we showed about this example, that it is actually a linear transformation. Now I'm going to show you again a linear transformation, not by doing the work we did before. So now show linear by finding a matrix A. So I want you to find a matrix A such that T of X is actually A times X. So another way to show that a transformation is linear is you try to find the matrix A such that T will be given by A times X. And we're going to do it by inspection because we can. It's fairly simple. So I want you to find me. So my question now is, give me a matrix A such that, sorry, I'm going to rewrite it. So T of x1, x2 is x1 plus x2 to x2. My question now is, give me the matrix A such that A times X will give you that. By inspection, can you give me the matrix for that? And the matrix entries of the matrix should not depend on x1 and x2. The entries should be constant. Can you give me the matrix that implement this transformation by inspection, just by looking at it?
Yeah.
Yes, who would like to give me this matrix?
Going by columns first, I'll do 1, 0, and then 1, 2.
1, 2. Do you agree with him? Check it out. x1 plus x2, absolutely. x1 plus 2x2, absolutely. A times x. So this transformation T is linear. You can automatically say it's linear now. You don't have to do the whole work because it's a matrix transformation. It's given by a matrix A. All right, so if you have a transformation and the question, is it linear? If you can find the matrix that implement this transformation, you can say automatically it's linear. If you can't find it, then you have to give me an example to show that the linearity is breaking. So one more example before we move on. Okay. So another example, again, a simple one. So I'm going to take the one I gave on the notes, but since the writing was very small, I'm rewriting it. So this is equal to x1 plus 2x2 plus x3 and minus x1 plus 4x2. And now my question is, show that this is linear by finding a matrix A that implement this transformation. So it means you have to find me A. All right. What size matrix is A should be? So I want A. I give you 1 minute to do it. You do it in front of yourself. And then I'm going to pick one of you to tell me. So we're going to write this A times X. Okay. Are you ready?
Yeah.
All right. Go ahead.
So A would have to be a 2 by 3.
2 by 3.
And that you want the entry? I'll do the entries by rows.
I don't. Yeah. Go ahead.
1, 2, 1.
1 to 1,
Negative 140.
negative 140. You agree with him? We multiply it out. x1 plus 2x2 plus x3 minus x1 plus 4x2 plus x3. Absolutely correct. Okay? Will A always be the coefficient of the transformation? Basically, yes, if I understand. They're going to be those. Is this your question, Alex? Yeah. That will be really the idea. That's going to be A. And if you cannot find those entries, make sure those have to be constant. And if you realize you cannot do it, and then most probably it's not linear, and in this case, you should have to give me an example to convince me that one of the properties of the linearity failed. That's really how it is. All right, so example of linear transformation. And for example, I added in example 6. Let's take the transformation that reflect across the x1 axis. So this is immediately linear. Let us remember that. What's the transformation I'm talking about? Let's suppose I take a transformation, I take a vector and reflect it across the x1 axis. So that's my t. It takes my vector x1, x2, and take it down to x1 minus x2. So t x1, x2 is x1 minus x2. Is this linear? Basically, can you implement it by a times x? What do you think? Yes or no? Yeah?
Yes.
Yes,
Yes.
it's very easy. 1,
0.
0,
0.
0,
Minus 1.
minus 1. That's the reflection matrix. We're going to find another way soon to find it immediately, but reflecting is a linear operation. And if you guys think a little bit about it geometrically, it is linear. So let us say one property. If you stretch this, if this vector go here, and if you stretch it by a factor of 2, let us say, it's naturally going to go right there. Immediately. That's linearity. 2u will be mapped immediately to here. That's one property of the linearity. And if you think about addition, it's going to also carry on. So if you take two vectors like this, and this is their sum, if you reflect that, and you reflect the other one, and those, you take the parallelogram that's formed by both of them, this sum here is going to be immediately reflected down here. So the geometry as well is actually there. All right. Now, a lot of transformation are linear. As I said, a lot of geometric transformation are linear. So reflection is linear. Respect the x projection is linear. Now the second part is of the lecture is, we're going to start it today, is that if I know somehow that my transformation is linear, like a reflection or rotation, which is rotation is going to be linear, how can I find my matrix? So if I tell you it is linear, geometrically, how can we find the matrix A? So we're going to start with the following idea. Matrix of a linear transformation. In this section, what we're going to show is that every linear transformation is a matrix transformation. So if it's linear, it will have to be given by a matrix. It has no choice. And we're going to find the matrix that implement the transformation. So there are two aspects here. We're going to show that. If you know it's linear, you guys should tell me to move my paper up and down, because sometimes I don't pay attention. So what this is going to tell me, if I know it's linear, like geometrically, okay, I convince you geometrically that my transformation is linear. Then what we're going to show that if this is the case, then the transformation will be given by a matrix. It means if this is the case, we should be able to find a matrix that said T of x equal A times x. And we're going to find out what is this matrix. That's really our goal. So we're going to show that if I know it's linear, and the application will be the rotation. I'm going to convince you geometrically, or convince yourself geometrically, that rotating a vector is a linear operation. The question is, fine, since I know it's linear, the first thing we're going to show that it is matrix transformation, and we're going to find the matrix that implements. So we're going to start with a little bit today. To get to that, we need the following definitions. Unit vectors in Rn. What's the unit vector in R2? All of you are taking calculus 1, calculus 3 almost by now. What are the unit vector in R2? The I and the J vector, correct?
Yeah.
Yeah. In this course, we're not going to call them I and J. We call those unit vector E1 and E2. So E1 is the vector 1, 0. So instead of calling it the I vector, and you will know why I cannot do that, I'm going to call it E1. And E2 is the vector 0, 1. E1, E2 are called the unit vector in R2. What's the property of the unit vector? If X is any vector in R2, can I write it as a combination of E1 and E2?
Yes.
Yeah, can I write that? Can any vector be written as a combination of E1 and E2? And basically, geometrically, it's easy. I mean, geometrically, there is nothing to it. If I have, this is my E1, and this is my E2, E1, E2, if I take any vector here, and not 2, 6, for example, so my vector 2, 6, I can write it as 2E1, because that's 2E1, and this is 6E2. So it could be written as 2E1 plus 6E2. So any vector in R2, if X is any vector in R2, then X, I can write it as X1 times 1, 0 plus X2 times 0, 1. It means X1, E1 plus X2, E2. That is, every vector in R2 is a linear combination of E1 and E2, and the weight are the entries of the vector. Okay. In R3, we can do the same, but in R3 we have 3 unit vectors: E1, 1, 0, 0, E2, 0, 1, 0, E3 is 0, 0, 1. All right, now in R4, how many unit vector are gonna have?
4.
4. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1. Okay, so the reason we cannot call them IJ in this course anymore, because we talk about unit vector in R3, in R4, and as you imagine, we ran out of letter to call them. So in Rn, we have n unit vectors: 1, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 1, and so on and so forth. Okay, so those are the unit vector in Rn. All right, I'm going to finish today's lecture with a small exercise, and then next time we pick up from the exercise. So my exercise is the following. You guys can write it with me. This is the simple problem we're going to do. I'm going to give you T from R2 to R2, let us say. And I'm going to tell you it's linear. So does T have this property? You know, we know a lot of linear, it's property. And I'm going to give you 2 information only, not more. I'm going to tell you that this transformation T is going to take the vector E1 to the vector -4, 6. And I'm going to tell you that it takes 0, 1. So I'm going to tell you what T does to the 2 unit vector, E1 and E2. 2, 1, 2. Okay, that's E1 and that's E2. E2. That's the only information. It's linear and it does this. And now my question to you, pick any vector. Somebody give me a vector. Somebody give me any vector. Anything. Go ahead.
3, 3.
3, 3, 3, 4. Okay. My question is, can I find what t does to the vector 3, 4? Watch what I'm giving you. I'm only giving you E1 and E2. And I'm telling you it's linear.
So
Can I
then
find anything?
yes. Yeah. And I think we would do is, since that's 3, 4, you just take t of E1 multiplied by 3 and add it to 4 times the transformation of E2.
Okay, let's see. How can I write 3, 4 in terms of E1 and E2? How can I write this? It's 3, 1 times 1, 0 plus 4 times 0, 1. Does this make any sense? Have I changed anything?
No.
No. Okay, it means let us just get rid of that, not get rid of that. This is E1 because I want you to get used to this notation. And this is E2. And now the magic of linearity. What that linearity tells me. Image of the sum is sum of the images. Plus that. Again, linearity tell me. So here I am using that linearity preserves vector addition. Now I'm going to use it to preserve scalar multiplication. So I'm going to take the 3 out, t of E1, plus 4 t of E2.
How do you decide if you're going to add the 3 and 4? Like what operations you're going to use with the t you're given?
Which one?
So you had t of 3, 4, and you just had to multiply it by 1, 0, and then add the 4 by 0, 1.
Mm-hmm.
So how do you decide like to do that? Is that so that way you can
yes,
get the
because okay, let me I will see if I answer your question, because I know only t of E1 and t of E2, right? Mm-hmm. So what I tried to do is to write 3, 4, the vector 3, 4, in terms of E1 and E2.
Okay, so you're trying to turn it into E1 and E2.
Exactly. I'm trying to write it in terms of E1 and E2. So, and the vector 3, 4 is 3 E1 plus 4 E2. So I can connect. Did that answer your question? It's a good question.
Yes.
Connect the dot. Very good. So now I'm almost done basically. Now I know t of E1 and I know t of E2. So this is going to give me minus 4, 6 and 1, 2. With me so far? Do I have an answer? Can I find t of 3, 4?
Yeah.
Yeah. But now I'm going to make something a little bit more interesting, and that will be the end of it. I'm going to rewrite this in the following format. Remember when we talked at the beginning of the semester, multiplication of a matrix times a vector. Who can find me the matrix? I'm going to stop talking. That should go here.
4, 1, 6, 2.
Repeat. Give me.
Or negative 4, 1, 6, 2.
Absolutely correct. Remember when we talked about multiplication of a matrix by a vector at the beginning of the semester? We say a matrix times a vector. We give 2 definitions. One, we call it the row column definition. And the first definition was a matrix times a vector is a linear combination of the columns of A where the weight are the entry of the vector. Means this matrix times this vector is 3 times the first column plus 4 times the first column. And what's going to turn out to be is, this is the matrix we're going to be looking for. So now what I showed you that t of the vector 3, 4 is actually this matrix times 3, 4. And this matrix is nothing more than T of E1 and T of E2. And that's the matrix that we'll be looking for. And next time, I take you exactly from there. But what this shows you that only knowing what happened to E1 and E2, I was able to find what T does to any vector I want. You guys gave me an arbitrary vector, and I was able to tell you what T does to this arbitrary vector. Okay, we stop right there. How did it go, guys?
It went well.
Well, were you able to follow?
Yeah.
I think it was pretty smooth, yeah.
Yeah, it was all right.
Since,
All right.
specific, like it really helps with the lecture notes. I just had one general question.
Uh-huh.
Because in this application, I was trying to record the lecture, but it says that like on your feed, it's saying that you're recording it. So I was wondering if you will be posting these lectures on the Blackboard.
Eventually, not yet. Eventually, I will.
All
I
right,
also tried
just-
recording. It says that the host has to allow
Yeah.
permission for you to record it.
Oh,
Yeah, so like,
okay.
If you hit record, it says please request recording permission from the meeting host.
Okay, I don't know where to. I am recording it.
yeah.
But you're gonna post it.
Eventually, probably,
Eventually.
yeah,
All right,
yeah,
okay,
yeah.
okay.
that
I
was-
am eventually, probably not now till the end of the week, not
right.
yet,
That's fine.
but eventually I will. Anything else? Please tell me any comments you have, because this is very new to me, as you guys imagine.
Are we
And
still
that-
doing weekly quizzes, or is that changing?
No, we're gonna do weekly quizzes. You have, can you also scan the notes you look today on Blackboard? I have the lecture on Blackboard already, Hannah.
Hmm.
Yeah, I have it. Did you see it?
Yeah, I have it pulled up on Blackboard as well. So
Yeah.
Yes, yeah. So the lecture is already on Blackboard. What I'm writing now is just basically the lecture, but because the lecture was written in a small print, because that's how I write, I decided to do it all over again. Next time I will have larger print.
I will say, since this is like very inconvenient method of just like teaching at such like a very short notice, like I'm assuming you're using a phone or a laptop camera, correct?
Yeah,
Okay, yeah. So the quality is if I can get everyone to just like agree with this or disagree depending on how you view it. But from my end, it seems a little blurry, but it's like
yeah. I had other
Visible.
comment telling me blurry.
Yeah, it's a bit
will-
blurry.
Yes, yeah. I have others.
the video quality isn't really
yeah.
that-
I just like you mentioned earlier. The good remedy for it was if you just like increase
resolution.
no. If she just increased the font size.
The what?
The font size, the way you write.
Yes. I'm gonna do that. Yeah.
Right.
I'm gonna do that. This is worse, right? I'm trying to play with the lighting in my room.
I personally think it's fine.
Okay.
The lighting's
Anyone-
fine.
Yeah, unless anyone else.
Lighting's good, yeah.
All right.
So what is your setup? My dad's just wondering because he's doing the same thing and he's just like drawing with his mouse on his screen and he thinks this would be a lot better to do.
It's hard to do that in math. Drawing on the screen, it's hard.
Yeah, so he's wondering like what are you doing? Like how do you have what camera are you using right now?
Actually, I bought a small webcam,
Uh-huh.
which is it has a stand. It's a small stand with a webcam on the top of it.
Okay.
Yeah, I
You
bought
just hook it up to your computer?
Yes, and I hooked to my computer. Yes.
Okay, thank you.
Yeah, because math, as your father, no, we cannot do it using whiteboard. It's impossible for me to do whiteboard.
Yeah.
So I bought last week a camera. That's why I didn't get back to you guys early on, because I had nothing to work with. So everything was figured out by Saturday, to be honest with you. So I was panicking the whole last week,
Uh-huh.
like everybody else. And but now it's working. I mean, I hope at least it's working.
I think if we all just pull up the Blackboard notes, like if they're in bigger font while she's
Yes,
writing
as
it
I
down,
said.
it'll be easier to
Right.
follow.
I told you that. I told you you guys have the notes, the lecture notes, have them, and next time I will write them in much bigger print. So we won't have any issue with that.
Yeah.
All right.
Okay.
Yep, thanks.
Anything else?
Are
Okay,
the
bye
quizzes
guys.
gonna
I have to go to my
Bye.
other class. Bye bye.
Bye.
Bye.